Alright, time for a draft physics.com video presentation. Draft science on YouTube and debate. What the hell happened there? Yeah, gotta fix that. Alright, where was I? Debatephysics.com. Also, where there's a bunch of 5-minute videos going over some of these principles. So I guess I'll title this "So there isn't so levers don't conserve momentum." So that's what they're proving. Okay, and I'm arguing, well, if they don't conserve momentum, you sort of have to explain where the momentum goes. That would be a simple enough obligation, considering Professor Lewin's overt statement that nature can deal with kinetic energy one way or another, but nature can't finagle momentum. He didn't say conditionally, so, but anyway, it doesn't matter. The battle continues. So, Ian Gosling has converted what was one apparent truth into some other apparent truth. All right. And he did it through this intermediate video where he rationalized the previous results and tried to say they're not what they look like. Okay. Because of parallax. Okay. And then he goes ahead and commits the very crime of parallaxing. Okay. So what's the point? So when it's to your advantage to use the word, you use it. It's just kind of a joke. But anyway, because he basically does the inverse parallax trick. But whatever. So we'll just play this little clip and then we'll get on with it. But yes, it's disappointing. I'm going to have to do the experiment because obviously, you can't trust anybody. And certainly, like, even if it isn't any shenanigans on his part, it's just some sort of incompetence and stupidity. The fact is that, it demonstrates, if this is the facts, okay, it demonstrates that, depending on how you point your camera, things will look entirely different. I mean, upside down different, almost. But anyway, so let's play this little clip here.
The arc of the pendulum. This is something like what we would see. Of course, it's all.
So the way he drew it is, number one, just that doesn't look anything like the picture you showed. Okay, the video doesn't look like these numbers, but whatever. Let's play along.
Parallax error, I think, with the camera was quite high looking down.
Right, but that should be to the advantage of the thing closer in the first place. So the thing further away is the thing always, kind of cheated by parallax. That's my understanding. And clearly in that first image, that's what you see. So let's show the first image again, and we'll just do a bunch of images, I guess. So I do have an arrow now, so I should be able to move the arrow. So this is where the half mass went. And this is, he's saying, is parallax, this distance we're seeing here. Where this is big and this is small or something. Somehow parallax has made this look so much higher than it actually is. And this, okay, this way down here. So we're comparing this to this. All right, and he's saying, and this one is behind. Okay, so let's just understand, this one is swinging behind the other one. It's further away from the camera. It's just a fact. So the other one's swinging back here, okay, a few inches behind this one. And we're supposed to believe that parallax made it look like this. So I'm just saying that's the start-off image. I mean, you can see the shadow this is casting. It's close enough to the board where you can see the shadow it's casting. Yeah, come on. So huge, gigantic, visually you'd say, oh no, that's a lot more than 0.4 higher or 0.5 higher or even twice as high. I mean, it's just saying that's the impression of the image. Okay, so he's saying honest cop style, that he did the experiment a second time, okay, and filmed it I'd argue, obviously you can't see the top of the table, so he's now below the table a little bit. I mean, he's like level with the table. You could argue if that's maybe his argument, but you're still having to look up to see the objects. So now, and he's got the camera a lot closer. So now parallax is in play again in the inverse. Okay. I mean, in this case, it should have cheated. Parallax should have made this look lower than it actually is, I would argue. Well, I should point to it. With the pointer, this should look lower. What did just got grouped? I didn't want to group anything. Hold on a second. I don't know, some sort of OBS thing. Anyway, I can't even just move something around without something fucking up. Anyway, all right, so we're there to there. Okay, just pretty much gigantic in terms of the perceptual difference. I mean, you know, this one looks like it's here compared to this one's here. This one's here. I mean, it's over the little clay line, you know. I mean, it just doesn't, it's hard to buy that is really just a very small amount of distance. Alright, so enough of that. We'll move on to the other images. So, from the new videos he's done, okay, so we'll get those images up. Alright, so there's the new image. Maybe I'll blow this up and just take a better look at both parts. So clearly not much of a difference here. This is probably realistic in terms of the height. So this is maybe twice as high. Maybe. Probably less than twice as high. Should be at least twice as high to make the 1.4 thing. So it's even indicating less than 1.4. So it's not like you lost half the momentum. It's less you lost 60% of the momentum or 70. Huge loss of momentum by this image's statement. And that's just it. So this is the same experiment. This is supposedly the same exact experiment as this. Now, that's hard for me to see. It's hard for me to see how parallax or any other image distortion. Now, this has been aligned. In one case, you know, you can align it to the tape measure because he moves the board. And that's part of the problem here. It's unfortunate that he has a moving part between the two experiments, and that sort of distorts everything, you know, in the sense that you can get two different views. But frankly, you're not going to get anything. This isn't any less dramatic no matter what image you use. And this doesn't change much either. But I'll show you the changing images, just to throw it in for context. But, oh, Jesus Christ. So you have that tiny difference is supposed to be what this is. So this is showing that tiny little difference in the heights. Same experiment, he says. I find it hard to believe. Okay. So now the argument now is that now he's filming it from a bottom angle. So the one closer is now going to appear to be much higher, and the one further away is going to appear to be much lower. That's what parallax does. And the closer you get, the more parallax you get, the more it screws up your view. So he moved the camera not only down, but in, and now has created this image, okay, of the experiment, where the argument was when he had the above image, it would give an advantage to the thing going higher, that's for sure. Anything going higher would be essentially closer to the camera, but it's also still further away. It's still back further. So I don't think you can use the argument of parallax as being the cause of this gigantic difference. And so the two experiments don't look like they're the same experiment, frankly. Like something else was changed in the interim. The length of the string, something else was finagled with. The distance on the lever, something else doesn't seem quite right. But whatever. We're just stuck with this mess of inconsistent results. So let's understand what we have seen him do is he did a clay experiment where he dropped the one mass from 4 times the distance of a 2 mass. So 2 mass goes 1 distance, 4 mass goes 4 distances, and they crushed Play-Doh the same amount. But he wouldn't show that video. He just would talk about how it must be wrong. Okay, so we have that. And we have Brozo's experiment where he did the same thing, a catapult, and he launched billiard balls. And he got a velocity result of 19 and 11. Meaning the heavy, the 2 mass, took 19 frames to get to a location, and the 1 mass took 11. Very close to 2 to 1. Very close to twice the velocity. Not very close to 1.4. Okay, so we have that experiment. Then we have the Mythbusters experiment with all of its flaws, unfortunately. And then I did mine without, again, sloppy. I don't present it as a piece of. It was mostly for my own, verification, and clearly much more dramatic than this appearance, this tiny difference. So that's the murky water we're sitting in. And the argument is they're saying, well, yes, they had the context of, obviously I did make a lever on my porch with a 1 mass, a 4 mass, and a 1 mass. So a 4 mass, 1 distance, 1 mass, 4 distances, and it oscillated perfectly. So somehow the momentum is conserved when it's oscillating, but somehow if I try to throw something, somehow the whole thing breaks down and it doesn't conserve momentum anymore. So that's the argument. And they don't provide any explanation for where the momentum goes. How does the momentum get destroyed? Where does it disappear to? Where does it leak to? So I guess their argument is that it leaks to the fulcrum or something, that somehow the fulcrum knows the lighter mass is really heavier somehow. So even though it weighs the same, it balances perfectly on a scale, somehow the fulcrum knows it weighs more and is now harder to push. That's their logic. I can't make any sense out of it, so I'm still stuck saying, no, sorry, I'm not buying it. All right. See if there's any other images that are worth displaying here. I guess I'll do just the superimposed of the 2 images. But, I mean, clearly these 2 don't look like the same experiment. Just doesn't look like the same experiment. Alright. I'll be back. Alright, so these are the two experiments superimposed. Now again, I have the same problem. These are 2 separate images, and you can see the tape measure in this case. There's 2 tape measures. And what I did do was get these things to match up. So because he moved the objects, you have to put the image together based on the fact that it did move. So the 2 images are but very slightly different. Now the truth is the half mass did go a little higher than this. I didn't catch the right, I didn't bother downloading the video and doing all that crap because frankly these differences not going to matter. I mean, a ½ inch up, a ½ inch down ain't going to make much of a difference, an inch even. But this is in the context of what are we really looking at? What is this really? But clearly, this distance is pretty much the launched objects start off. Let me use the arrow. They start off here, so they really are the top of them pretty much even with this line. So you can argue this is the real distance, okay, the height distance that it traveled, so this distance would be the same idea, that you'd really have to measure from the bottom to this top of this line. The bottom would be all the way to the bottom down here. So at best, you could argue that this is 1, 2, 3, 4. 1, 2, 3, 4. Yeah, it almost is. So because I was a little bit shy of its peak, so let's just say this did reach the 4 line, and clearly this is I don't know if it's that clear. Okay, clearly it's one, some extra above the 2 line, and so that's only 1.5 the height. You know, it's not twice. I mean, it's not 4 times the height. It's 2 to 4, so it's 1/2 at best, as stated. So, yeah. But how much of the view has been distorted by the fact that this object is forward and this object is behind. And the object behind is going to be definitely look less impressive from this camera angle. It's going to look less high. And the forward object is going to look higher because of parallax. Okay, the very thing he claimed a right to claim, and now he will say, I don't have a right to claim it. Okay, I don't have the right to bring it up. He did, but I don't. Okay, that's the double standard. All right. So that's, you know, like I said, I'll just show you the other image where I lined up the tape measures, and you see there's really not much difference between the two. Alright, so now you can see that the tape measure is okay, and all this other stuff now is doubled up. Okay, so because he moved the whole board, which is, you know, again, not ideal. But anyway, you got the same kind of basic idea here. Yeah, now it says like that's 2 notches, but that would be, yeah, you have to measure from the top to the top, I guess. So it's 2 plus, and this one is 1, 2, 3, 4. Yeah, 4 minus. But this did go a little higher. Like I said, I just didn't grab the greatest still. But again, it's not nearly enough to change the math or the understanding that it's clearly nowhere close to 4 times higher, and that's what it should be with twice the velocity. So it's clearly not going twice as fast, and that might be argued that that's a flaw in his system of pushing. So again, he did use kind of a short lever. The longer the lever, the better, and to maintain contact with the object and all of that crap. But whatever. Like I said, I'll try to do the experiment eventually, and that'll, again, you know, how much will it help? Because how much better can I do it? I mean, I'm sure I can place my camera in angles that'll provide me an advantage, and I'm sure I can, you know, do all my fudging in my direction and create results. But everybody will just believe that happened anyway. Even if I don't do any of that, that's what they'll believe I did. So what's the difference? Again, physics really should have, all these experiments should have already been done, but just understand what they're claiming. So the claim is that you don't have to conserve momentum, which to me is a pretty dramatic statement being made. Not conserving momentum. Big statement. You know, and you have to account for that. You have to explain where you lost it. Why? Why does the lever not conserve momentum? Why? Alright, wait. In this case, we might be just saying springs don't conserve momentum. Okay, so might not be the lever's fault, right? Because he used a spring. Now, I did use elastic bands. There really shouldn't be that much of a difference. But clearly my experiment didn't look like his. So, you know, well, Brozo used a spring. So, it seems like springs should be able to conserve momentum. Yeah. But it's a real point to make. Is there something about the spring that just can't manage? It's the same exact motion of the lever, frankly. So I don't know how the spring could not see it as the same weight. I mean, theoretically, they're the same weight. I just don't know how you get past that argument. If I have something that weighs the same, I mean, it weighs the same on the balance. It weighs the same. So twice as far out on the lever, your weight is double. It's just a fact. So I mean, how could the spring know that, oh, that's a fake weight? It's a weight. It can't be a fake weight. So again, I can't there's no, until they provide some sort of explanation how they can get around that. That somehow it isn't weighing the same when every scale you could measure it on is saying, yes, it's weighing the same. That's what the scale is saying. I put the two things, the two mass here, the one mass twice the distance, they weigh the same. How does the spring know they don't weigh the same? How does it figure that out and somehow retard its function? When it's supposed to do exactly the same thing it would do with the two mass. The two mass at half the distance weighs the same. It applies the same resistance to the lever. How can it produce any kind of different result? Doesn't the spring have to move exactly the same? So I guess another advantage here would be to film over the top of the lever, but I just don't know if its camera's good enough for that, because that's kind of a high-speed motion. So that's something where you need the 968 frames of, physicist Michael's Samsung, whatever the hell it is, camera, Galaxy something or other. That would be an advantage. But anyway, for now, yeah, we're okay. Advantage, now disadvantage. Okay. So that's all. We just thought the ball moved a little forward, but no, we're just back where we started, unfortunately, 2 days ago. So that's the only way I can look at it until we see some better data. Okay. But yes, I mean, it's clear what we do see from that first image I showed, okay, where the two are side by side, is that yes, camera angles can make a huge difference, and that's a little disturbing that it can be that much of a difference. Just change the camera angle and you completely change what it's saying as a statement. So I'll leave it there, and I'll just continue doing what I'm doing, which is requesting that people make a rational response to my query. So you believe you don't have to conserve momentum, and when you don't conserve it, you don't have to explain where it went. Because to me, that's, you really do have to explain where you lost the momentum. But anyway, till the next time and such and so forth and whatnot.